Hello everyone, we are from group 3, are going to explain about application of ordinary differential equations to electrical circuits.
Before that, let we introduce ourselves. My name is Puspita Dewi.
My name is Linda Kamelia.
And I am Rio Bimantoro.
And the next is electrical circuits. A simple electrical circuit is a series circuit. This circuit consists of the first, a battery or generator that produces electromotive force E times M times F divided to voltage or potential of E volts. Second, an inhibitor resistor with a limiter of R ohm. Third is an inductor with an inductance of L Henry, a capacitor with a capacitance of C farads. The current I measured in amperes is the instantaneous rate of change of charge Q on the capacitor measured in coulombs against time. That is, I equals to dQ over dt. This is the picture of series RLC circuits. From the basic principle of electricity, we obtain the potential generated in the resistor is ER equals I times R. B, the potential generated in the inductor is EL equals to L times DI over dt. C, the potential generated in the capacitor is EC equals Q over C. Because IT equals dQ over dt, then EC equals 1 over C is integral from integral IT dt from 0 to t. Kirchhoff law, the algebraic sum of the currents flowing into a deviation is 0, and the algebraic sum of the potential generated along a closed loop is 0. And the next is RL circuits. For the RL circuit, as shown above and based on Kirchhoff voltage law in A and B, the equation model is obtained di over dt plus R times I equals ET. And this is the picture of series RL circuits. The first case is if ET equals E0 or constant, then from the equation D, the equation model is obtained di over dt plus R over L times I equals E0 over L. The above dE is a linear differential equation of the form dy over dx plus py equals q. Solving the linear differential equation is by multiplying the integration factor mu e power integral p dx in equation dy over dx plus py equals q become mu dy over dx plus py equals mu q. And then we get d multiplied by mu times y equals mu times q dx. If integrated, then we get mu times y equals integral mu times q dx plus c. And then we get y equals 1 over mu integral mu times q dx plus c. So that the case it can be stated that it equals e powered in negative integral r over l dt, integral e0 over l, e powered integral of r over l dt, dt plus k. And then we get e0 over r plus ka power negative r over lt. If t equals infinity, then ka power negative r over lt is 0. So it is equal to the boundary value e0 over r. The specific solution to the initial condition I0 equals 0 is it equals e0 over r times 1 minus e power negative r over lt. And the next case, if et equals E0 sin omega t, then from equation D, the model equation obtained di over dt plus r over L times I equals E0 over L sin omega t. Solving the differential equation with integral factor is y equals 1 over mu integral mu times q dx plus c. Mu equals e power integral r over L dt. Yx is it. Q equals E0 over L sin omega t. Then we get e power negative r over Lt E0 over L integral sin omega t e power r over Lt dt plus k. Integral sin omega t e power r over Lt dt solved by partial integrals. Standard formula of partial integrals is integral u dv equals u times v minus integral v du. If u equals sin omega t and dv equals e power r over Lt, v is L over r times e power r over Lt, then we get negative omega L over R times L over R times e power R over Lt times cos omega t plus omega L over R integral sin omega t e power R over Lt dt. Next will be present by Linda.
For simplification, let A equals integral sin omega t e power r over Lt dt. Then we get A equals L over r e power r over Lt sin omega t minus omega L over r times L over r times e over r over Lt cos omega t plus omega L over R times A. And then we get A power R over LT over R square minus omega square L square times R L sin omega t minus omega L square cos omega t. Next. So that we find the IT equals E0 over R square minus omega square L square times R sin omega t minus omega L cos omega t plus KA power minus R over L times t. An electrical system is said to be in a steady state if the variables describing its behavior are periodic or constant function of time, while the system is said to be in a transient state or unstable state if the system is not in a stable state. The variables that describe the state are called the steady state function and the transient function, respectively. In case A, the function r power A0 is the steady state function or solution, while in case B, the steady state solution is the first term. For the example, a series RL circuit known to be R equals 10 ohm, L equals 2 Henry with a voltage source A is connected as shown in figure. At t equals 0, the switch is closed and current IT0 equals 0. Determine I for t greater than 0 if A equals 40, B A equals 20, A power minus 3, C A equals 50 sin 50. For the solution, based on Kirchhoff's law, the sum of the voltage in the closed loop in the equal to 0 so that VR plus VL minus A equals 0. So we substitute the VR equals 10 I plus VL to GI over dt minus A equals 0. We get di over dt plus 5I equals E over 2. So the solution of the above dv is for A, if A equals 14, dA becomes di over dt plus 5I equals 20. If it equals 0, so integration factor u equals A power integrates p dt equals A power 5t. And then we multiplying e power 5t by e, then we get A power 5t times di over dt plus 5I equals A power 5t times 20. So we get I equals 4 minus 4a power minus 5t. For p, if e equals 20, a power minus 3t, Ga becomes Ti over Gt plus 5i equals 10a over minus 3t when I t equals 0 by integration factor u equals a power pgt equals a power 5t. And then multiplying a power 5t by dA, then we get a power 5t times Gi over dt plus 5i equals 10a power 2t. And then we get 5a power negative 3 minus 5a power negative 5t equals 5.5 times a power negative 3t minus a power negative 5t. Then for C, if A equals 200 sin 5t, Ga becomes Gi over dt plus 5i equals 100 sin 5t. And then by integration factor u equals a power integral pdt equals a power 5t. We multiplying a power 5t by dA, then we get a power 5t times Gi over dt plus 5i equals 100 a power 5t sin 5t. And then we get a power 5t times I equals 100 integral of a power 5t sin 5t dt plus a. Integral a power 5t sin 5t dt, so with partial integral, and then the standard formula of partial integral equals integral u dv equals u times v minus integral v dv. If u equals a power 5t and dv equals sin 5t, so we get v equals minus 1 over 5 cos 5t. Then integral a power 5t sin 5t dt equals negative 1 over 5 a power 5t cos 5t plus integral a power 5t cos 5t dt. Then for simplification, let a equals integral a power 5t sin 5t dt, then we get a equals negative 1 over 10 a power 5t cos 5t plus 1 over 10 times a power 5t sin 5t. So that we get I equals negative 10 cos 5t plus 10 sin 5t plus 10 a power negative 5t.
Okay, now is about RL circuit with analysis approach. When the switch is connected, and based on Kirchhoff law, the voltage equation in the circuit can be expressed by E equal to IR E minus IR minus L di over dt is equal to 0 is become E equal to IR plus L di per dt. We define Y with E over R minus E so that dx is equal to minus di. So we can write the equation become dy over y is equal to minus R over L dt. Then by integrating we get y over y 0 minus is equal to negative R over L dt. And then we know that the t is 0 and the value of y is equal to y 0, and we remember that I is 0. So in general, the above equation can be expressed as I equal to E over R times 1 minus E over minus RT over L. Next. This is with numerical approach. When it's with connect, the equation can be expressed by Ti over Tt is equal E over L minus IR over L. And then by Euler method, the equation can be arranged to I times T plus delta T equal to IT plus I delta T times E over L minus ITR over L. Then in general, the above equation can be expressed as this is the step by step in step by step I, that is I plus 1 equal to I equals under I plus delta T times E over L minus IIR over L. Okay, nice. Then this is the new example. There is an RLR circuit composed of a resistor with a resistance of 2000 ohms and an inductor with an inductance of 4 Henry is connected to a voltage source of 10 volt. And we can analyze the flowing when the switch is closed or is on using analytical and numerical analysis. Then the delta here is the delta T here is 0.01 millisecond. And then to show the solution, we must declare the variable in equation. We get the resistor is 2000 ohm, the L or the inductor is 4 Henry, the E, there's no epsilon, there's E, is 10 voltage, it is from 0 second, and the delta T or the gap of the time is 0,00001 second because it convert from 0,01 millisecond into second. And then we substituting the variable into the formula of analytical and numerical methods. Then next, we get the result by using Excel, and we can see that the I of analytic and I numeric is not the same, but it's close enough. It's very close. It's detailed close because there is less than 0,0001. It's so less than that, and then the time is so detailed also. And commonly, the analytical result is less than the numeric result. So we can use numeric result instead of the analytical result. We calculate the time from 0 until 0,0003 second. It's doesn't value of 1 second but 0,00 because we must see the detail and the difference between analytic and the numeric for the small value.
Okay, that's all the explanation from us about application of ordinary differential equations to electrical circuits. We apologize if there are any mistakes. Thanks for watching.